Good evening, everyone. Welcome to the Aquarium. I'm Jerry Schubel, president of the Aquarium. It's great to see all of you who are here in person, and I want to welcome those who are watching remotely. For those of you in the theater, please turn your cell phones off or put them on vibrate and refrain from texting for the next hour. I want to acknowledge our lecture sponsors, Gazette Newspapers and the Courtyard Marriott. And tonight it's a real pleasure to welcome Tyler Phelps, who's going to discuss his research on mesophotic coral reef ecosystems. He got his start here. He lived in Long Beach, and he was a volunteer here. He used to come to lectures when he was a volunteer, and now he's come back to give one and show us how to do it right. That's what he told me, right? He's a graduate student with the California Academy of Sciences in San Francisco, and he's getting his master's degree at Cal State San Francisco. He volunteers with the U.S. Coast Guard Auxiliary, and when he was here, he was in the VolunTEEN program. He got his bachelor's degree from the University of Hawaii at Hilo, and it really was fun to hear some of his stories over dinner, and his parents and his grandmother are all here, and a number of you are his neighbors and fans. Please join me in welcoming Tyler Phelps.
Hello. Oh, testing, microphone on. Everybody hear me okay? Okay. Well, once again, my name is Tyler. I grew up in Long Beach here. Went to high school, Wilson High School. And grew up with the Aquarium. So I attended this lecture series when I was in middle school and high school. And so it's a real honor and pleasure to be here and be humbled to come full circle and be a speaker for you tonight. So before I get started into my lecture, there we go. I wanted to do a couple acknowledgments. First and foremost, my parents, Steve and Joyce Phelps, are here tonight. It really takes parental support and loving nurture to encourage them to go on and do more adventurous things that I'm pursuing. So I really want to thank them from upbringing, from walks along the Long Beach Peninsula when I was less than 5 years old till here now. Secondly, I wanted to thank Linda Brown and Claire and the rest of the Aquarium staff, Dr. Schubel for hosting as well, of course, for making this lecture series possible. And also Dave Vandervoort, who's in the audience as well, for introducing us and made it possible for me to be a speaker with you tonight. I want to give a shout out to my teachers and mentors, some of who are in the audience, for all their support and encouraging me up to my development into a career in marine biology. A special shout out to the mesophotic team with the California Academy of Sciences. I'll introduce them now, and you'll see pictures of them more throughout the presentation. With the hammer, that's Bart Shepard. He's our senior director. He's the boss, so he gets the hammer. Next to me, making the Tyler's all grown up face, that's Maria Isabel, our dive safety officer. Next to me, on the right side of the screen, is going to be Hudson Pinero, who's a postdoctorate in the ichthyology lab. And the right side is Dr. Luis Rocha, who's the principal investigator and curator of ichthyology at California Academy of Sciences. And a special kudos to him, if he's watching, for letting me shamelessly take all of his pictures for the presentation tonight. Also shouts to the Diving Safety Program of the California Academy of Sciences, our support divers especially, and the generous donors of the California Academy of Sciences Hope for Reefs initiative, which I'm going to be presenting all of our research, or some of our research, throughout this evening tonight. So a little overview of what we're going to be talking about. So at first, it's going to be a little bit about myself from the AOP to deep beneath the sea, so how I got started in Long Beach here. And then going to mesophotic coral reefs, explaining about their interesting ecologies and a little bit more about these unique ecosystems. Explaining and introducing the California Academy of Sciences, if you're not familiar with our facility up in San Francisco, our Hope for Reefs initiative, which we are on track for completing, or are currently pursuing right now, some of the mechanisms that are required for us to dive into the Twilight Zone using advanced mixed gas closed-circuit rebreather technology. And then I'll take a little behind-the-scenes tour of what it's like for us on expeditions. We do about 5 to 6 international trips per year, so I'll take you through a day in the life on an expedition with us. And I want to answer one of the most frequently asked questions I get in my personal life is, what's it like to describe a new species? And because we've been fortunate enough to have many new species on our ambitions, and kind of go over that process of what it's like to describe a new species with you tonight. And then lastly, some of our other current research initiatives that we'll be continuing to pursue in the coming years. There we go. So like I said, I grew up in Long Beach originally. This is me, and if I'm going to date myself here, if you notice on the lanyard here, that's a 10-year anniversary pin on my VolunTEENs badge. So I love doing the little shark lagoon, the wading with the little kids in the shark tanks. So I spent about 250 volunteer hours here growing up in high school. I attribute a lot of my upbringing in marine biology to the aquarium. I was one of those guys that was just kind of awestruck with the divers and the exhibits, and not everyone's thinking I could be doing that one day, but always trying to figure out how is this seal-like looking thing breathing underwater. So that kind of got me interested into doing scuba. In Wilson High School, I was a genuine fish nerd on the Marine Decathlon team with Mr. Campbell, and we competed at USC in our Ocean Sciences Bowl. So that really got me going on to taking that next step into wanting to make that career and going into college. So I went to Soka University for 2 years, studied marine science, and really developed my passion and interest towards research. So I realized a liberal arts degree wasn't going to get me to where I wanted to go for a PhD and have my own lab someday. So I transferred to University of Hawaii at Hilo, pursuing fish ecology in the marine science department. I was in Hawaii for 5 years until yesterday when I moved back to Long Beach. So now a little bit into these interesting ecosystems that I learned about in undergraduate that really kind of catapults me towards pursuing this for a full-time career. If you look at this reef picture here, we know the upper 200 feet of coral reefs pretty well. I mean, we see all those glamorous photos and pictures. And scuba, as far as scientifically, we know quite a bit about them to about 200 feet. Beyond 200 feet, there's a little more phenomenon at play, a little bit more considerations, a little bit more risk. So the recreational limit for scuba divers is 130 feet, but we want to generalize and say we explore pretty regularly to 200 feet on scuba. Now, who's to say, of course, that we have lots of divers every day, technical divers going beneath 200 feet, but I'm talking about a scientific standpoint. We only know much about them for the upper 200-foot range. And then going on beneath those, these habitats into our submarines. We have submarines going to a starting depth of about 500 feet. I asked one of the submarine operators on a research ship I was on in Bermuda, why is it that, why can't you go shallower than 500 feet? Why I always hear this 500-foot cutoff mark, why can't you go shallower? And he explained for two different reasons. The first being safety. They actually do not do very well, depending on what submarine you're using. They don't do very well with the ocean swells. So they want the deeper water. There's very minimal orbitals of water movements, so it's easier and safer to operate the submarines. Also, temperature-wise, in these 1 atmosphere ambient pressure submarines, it gets very warm. If you're spending this above the thermocline, it's very, very hot inside these submarines. The last reason why is submarines cost about $30,000 per day to use. So if you have a wonderful research project with that funding, you generally don't want to spend that kind of money farting around the shallows. You want to take the submarine as deep as it goes to find something really remarkable. So what we're left with is a range, this Twilight Zone of mesophotic coral reefs, or the Twilight Zone, between 200 feet and 500 feet. And there's really interesting habitat, actually, due to the last glacial maximum. So 100,000 years ago, we had miles of ice on our tectonic plates. And all that water uptake in the ice left the oceans a lot lower in sea level. So about 300 feet, actually. So our sea levels were about 300 feet deeper, deeper than they are today. So we actually see these drowned coastlines and these drowned coral reefs. It makes very interesting habitats. So I learned about this presentation from Dr. Richard Pyle at the Bishop Museum. And in his presentation, he said that his team was finding about 12 new species per hour of dive time at these depths. And I thought to myself, wow, for somebody that wants to get into a career of marine biology, how exciting it would be to find a new species and describe it. And that's the kind of thing that combines my interest for adventure and that adrenaline rush, but also to have the fulfillment of me making a contribution to science. So that's what really got me into mesophotic coral reef ecology. And a little bit about, at the same time I heard about mesophotic coral reefs, I learned about the California Academy of Sciences, and they've been around since 1853, but their mesophotic initiatives began about 10 years ago. So when I was still at Hilo, I learned about their incredible scientific diving program, making these dives to 400 feet plus, and these rock star guys finding new species. So I got connected with them over the course of my career and me at a conference. But a little about the Academy is we're based in Golden Gate Park in San Francisco, California. We're a planetarium, the Steinhardt Aquarium. We have an aquarium as well. It's a rainforest as well in the aquarium under a living roof. The green structure on top is a living roof, so to speak, and a natural history museum. So our collection has over 26 million specimens. So we have quite a large catalog of specimens that various researchers can request that from our collection to be sent out to them for them to do their own research on. And one of the things at the Steinhardt Aquarium right now at the Academy is we have the Twilight Zone Deep Reefs Revealed exhibit. So this is a place in our aquarium where folks can see fish that don't have names yet. So we use through our various projects, we developed different types of containment systems to bring these fish and organisms up from 200 feet, 500 feet depths, and display them on exhibits to bring awareness to these beautiful reefs that you'll see tonight, which makes them relatively spectacular to study. And a little bit about the Academy as far as our objectives. So the Academy Sciences, we strive to address one of the greatest biological challenges of our time, which is to prevent the ongoing degradation and potential collapse of the world's coral reefs. That is one of our largest threats we're facing as a society. And our Hope for Reefs initiative, which is what our funding and our projects is based out of, is to explore, explain, and sustain the world's coral reefs by making fundamental breakthroughs in coral reef biology, developing new transformative conservation solutions and restoration techniques. And sharing those, of course, what we know through innovative exhibits and educational programs like the Twilight Zone exhibit. And so here's a little snapshot of some of the remarkable fishes we're finding at these depths. So you're thinking, when we think of something that's deep, maybe you think of those alien-looking organisms from the Mariana Trench, but the fish in the mesophotic are very colorful, they're very ornamental and attractive, and because of that, they also have a lot of value to that. Meaning monetary as well. So some of these new species that we're describing, some of the ones for extreme aquarium collectors, they're spending upwards of $10,000 per fish. I mean, some of these are truly beautiful. I want to highlight a few of them. This is a Borbonius photographed in the Philippines at about 400 feet. This is an Odontantheus Katayama, which is at 140 meters. That's about almost 500 feet. This is a Centropyge abi. This is photographed in Palau. Again, another very deep water speed, about 500 feet for these guys. This is a Balanoperca pili. This is a soapfish, very funny-looking guy, and we actually nicknamed it the Dr. Seuss fish. Richard Pyle described it. And one of my favorite ones, Sakura speciosa. Sakuras, all these very beautiful fish we're finding at these mesophotic depths. So even though they're relatively hard to reach to, doesn't mean that they aren't holding treasure troves of biodiversity and different species. And I didn't want to exclude the benthic audience, part of the audience too. So this is a benthic picture from the Bahamas, and you just see all kinds of rainbow troves of sponges and algae. So these reefs have lots of biodiversity and lots of different species we can learn about them. So if you're wondering, like Mark Lane, he's our senior dive officer, this is on a fishing boat we chartered in Easter Island with all this kinds of gear. How are we doing? Why are we doing this? Well, I think he's actually wondering why don't we have a bigger boat. But how do we do these types of dives, and how are we getting to these unique species and finding these new ecosystems? So this is going to be a little bit of a review for the divers in the room, but I wanted to touch a little bit on kind of diving physiology 101, on how we can do these depths. So traditional air we breathe consists of a 21% air and about 79% nitrogen. There's 1% trace gases we're going to loop into the nitrogen component. And when we descend even in the pool, even as deep as 1 foot, the ambient pressure that we're breathing the gas at is going to push the gas into our tissues. We're going to on-gas the gas we're breathing from. So in this case, the nitrogen is the one we're concerned about because oxygen we can metabolize. So the nitrogen is going to enter our tissues, and that kind of determines what happens next. So we have this gas we're breathing, and as we go down the water column, or as our depth increases the deeper we go, we have an increase in partial pressure. So as the partial pressure increases, Henry's law tells us that the gas is going to be absorbed in relation to the partial pressure of the gas we're breathing on. So essentially, the deeper we go, the higher the partial pressure on the gas, and the faster that gas is going to be absorbed into our tissues. So there are different solutions. We can remedy this problem. If we want to go deeper, if we want to stay longer, we can try to replace the amount of nitrogen. So say we try enriched air nitrox. We're going to replace some of the nitrogen we're breathing so we can stay down longer with oxygen. And one of the benefits of that is it gives you more energy. So the verbiage goes, you can stay longer, feel stronger. So we can add oxygen to the mix, reduce the nitrogen, so we have less nitrogen going into our bodies. In theory, we can now stay longer. But the problem with that, though, is the increase in partial pressure now on the oxygen. So as we descend in the water column, the partial pressure for the oxygen is going to increase even faster. Our partial pressure is going to increase even faster than the oxygen. So oxygen actually becomes toxic to us at depth. So at 20 feet is actually the limit we can breathe pure oxygen to. So all the time we hear folks saying, use oxygen for scuba, but that's not true. The oxygen tank is actually air or some other gas. Very rarely do we use oxygen in scuba unless we're using it as a decompression gas. So there has to be a solution to this problem we have. We can't go deeper if we're replacing this nitrogen with oxygen. So we want to avoid our oxygen toxicity. We want to avoid our narcosis. So narcosis is a phenomenon that happens when we breathe the nitrogen in our mix. We breathe it deeper, the nitrogen becomes narcotic to us. So we get kind of this loopy, almost like you're drunk underwater. So we want to replace the nitrogen with a better gas. We also have to reduce the amount of oxygen now so we can descend deeper. So the solution to that is we call trimix. And trimix is now we're adding a third gas to the equation, and that's helium. So we have, in this example I have, 10% oxygen, 20% helium, 20% nitrogen, 70% helium. So we have lots of helium in the mix. So because there's so less nitrogen, we now have less of it going into our bodies that affects any sort of decompression we might have in consideration. But we have lots of helium now. But the good thing about helium is a very small molecule. It's the second smallest particle in relation to hydrogen, and helium's inert. So the good thing about helium is as it enters our body, it leaves our body a lot quicker than nitrogen. So the downside to this, though, as we descend deeper on these dives, is that the cost per dive increases dramatically because helium is a very expensive gas. So as we ascend deeper in the water column, the cost increases. And to give you guys an estimation, if we're doing, this is myself doing a open circuit decompression dive with 4 cylinders, and if we were doing a 300-foot dive, it's about $300 for one dive. So it's very cost ineffective. So our solution to this problem is rebreathers. So rebreathers, because we're only metabolizing 5% of the oxygen we breathe with each breath, the rebreather recirculates and rebreathes the gas we're going through. So this is the rebreather we use. It's a Hollis Prism 2. It's a closed-circuit design, which means that it has a series of one-way valves. So if we look at our diver here, he's exhaling. The gas is going around in a clockwise motion, and as he's exhaling around, it enters what's called a carillon. So instead of the gas going up into the water column making bubbles, it goes into our carillons, goes back down through a scrubber, and the scrubber is a mixture of called softener lime, and it makes a chemical reaction that binds the CO2, and that removes the CO2 from the mix that we're breathing, and then it gets passed through a series of oxygen sensors, and then we can add oxygen through the solenoid if needed. And the nice clean scrub gas comes back on our inhalation side. So essentially, doing this design, we can spend upwards of 8 hours underwater using just these 2 small 19 cubic feet or 30 cubic feet cylinders on our back. Some other benefits to closed-circuit rebreathers as well is they're bubbleless. So they make a lot less noise than scuba. So we can get a lot closer to the animal life as well for studying or for video, for photographers. I particularly love rebreathers for that. Also, we're breathing a continuous partial pressure of oxygen. So versus nitrox, you have that initial good feeling of energy from the gas you're breathing from the oxygen content. With closed-circuit rebreathers, we actually have that continuous throughout the dive. So when you get off a rebreather dive, it feels like you just already run a marathon. You have all this energy from that hyperbaric benefits. So here's a rebreather kind of dressed and ready for a dive. This is my unit ready set up. So you can see the hoses and the corrugations that trap the water. We have different manual addition valves that we can control the oxygen percentages as needed. We also, importantly, have what's called a diluent side. So as we descend deeper, the oxygen we're breathing that's in our loop that we're breathing is going to increase in pressure due to the depth we're descending to. So we need a diluent gas, something to dilute the pressure of oxygen. So it's something that has less oxygen. Usually that's where the 10% oxygen mix comes into play. And on the back, you see of the rebreather, this white material. That's going to be the scrubber that removes the carbon dioxide. And on this, we have lots of redundancies for the closed-circuit rebreather as well because it's so important to know what's our partial pressure of oxygen. There's kind of the sweet spot when we're diving a rebreather. So if we're less than a certain degree, say 0.4, we can become hypoxic and pass out from too less oxygen. But if we have too much oxygen, say above 1.6, we can have convulsions and seizures underwater. So it's very important. We want to know our oxygen. And so we have that information on our heads-up display, which sits right on our eye level, so we can't ignore it. We need to know it at all times. And it also becomes very handy when we're doing fish surveys. When we're constantly looking at the reef, we can just look, and our display has the information right there. For these deep dives as well, you see we have lots of different redundancies. So this is me doing a pre-breathe or a pre-dive check in Palau, and I have the near-eye retinal display on my heads-up display right here on my eyepiece. I'm verifying. I also have a secondary controller on my right arm, and then my left arm I have a backup computer that's just a standalone unit. So lots of different redundancies for the increased safety of what we're doing. And so here's some to highlight some of the expeditions we've done with the Academy. Here we go. So these are some of the projects we've done over the past few years. Bahamas, Bermuda, Curacao, Grand Caymans. We've been going to the Philippines for a long time. I want to say it's on the order of magnitude about 10 years. I know I'll get corrected on that later from the guys at the Academy. Vanuatu, Pohnpei, Palau twice, St. Paul's Rocks and Trinidad off Brazil in the Atlantic. Easter Island was last year, and we just returned from Guam 2 months ago. And some future expeditions we have coming up for the following years. Majuro, which we leave for in August, that's in the Marshall Islands. Zanzibar and Mauritius, Maldives. Indian Oceans are kind of our next big objective we want to try to investigate because virtually no mesophotic research has been done in the Indian Ocean so far. So that's been kind of our driving motivation to go to the Indian Ocean. And so now that you've kind of seen a little bit about our team, what kind of projects we're doing, what kind of equipment we use, let me take you for a test dive with us on expedition. So step one kind of starts with permitting. It takes months before an expedition begins to get our permits approved. So it's unfortunate that it's so much easier nowadays to just get a fishing license to go kill something, but it takes so much more effort to get a permit to actually do research and studies at some areas. So that's been our biggest limiting factor. If somebody asks me, why haven't you gone here? Sometimes it's because we can't get permit to do our research there. And other places, such as the Middle East, rebreathers are considered military technology, so we actually can't dive there because we operate on closed circuits. So this is what my living room floor looks like before an expedition. And you see one bag is full of the rebreather, which takes up about 50 pounds, unfortunately, to itself. On the other bag, it has, on the left side, all the safety contents are SMBs, our markers, the way we communicate to the topside surface. We have wetsuits and kind of save-a-dive kit personal items. A carry-on bag, which I always go over. Don't tell the airlines people I say this, but my carry-on is generally about 40 to 50 pounds in steel back plates for the rebreather and then at least 3 regulators for our different bailout gases. So what we're left with here is a little bag of clothes, about 3 or 4 T-shirts, a couple of swim trunks, 1 towel, and then applesauce, which I'll get to. It's a very important part of our diet, so I'll get to that a little bit later. And so you can see this is just for 3 of us here. I believe we were in Chile, Mark, Maurice, and I. So this is 3 of us each with 3 bags. So you can imagine this gets exacerbated when there's 7, 8 of us on expedition. So we don't travel light, unfortunately. So our next phase out on expedition, our first day is unloading all the stuff we have to ship. So some places like Easter Island, they didn't have the oxygen content that we needed to do our gas blending. So everything had to be done in advance and shipped to destinations. And I was mentioning earlier, before this evening, we also have to take other safety considerations into account. So in Easter Island, for example, they didn't have a hyperbaric chamber on island, and the Navy wasn't willing to work with us on letting us use it in the event of an accident. So we had to bring our own hyperlight, which is a portable decompression chamber, with us. So a lot of logistics goes into months in advance. So we unload all of our equipment, blend gas as we need to, which is what Maurice is doing in Guam here. And then we also set up the scientific equipment, which are our little monitoring structures, which I'll mention later this evening too. So a lot of prep work goes into on the first day. So we really hit the ground running. Day 1, our first dive day, 6:30. It's breakfast time, so coffee, very important. Sometimes we have to bring our own if there's not good coffee where we're going to. I want to mention that Bart did not finish all of his pancakes. This was in Guam. 7:30. We start prepping our units. So going through our checklist, there's lots of nuances to rebreathers. So we want to treat this more like flying a plane, the way pilots do when they're going through a pre-flight check. We do the same thing for our pre-dive checks. So we have lots of a big checklist we go through, make sure all of our steps, make sure the unit was assembled correctly, our gases are programmed into our computers and everything like that. And then we have what's called the pre-breathe, and that's before we get into the water, we're running through our electronics, making sure everything's working correctly. We're warming up the carbon dioxide scrubbers, making sure they're ready for us for our dive. So it's kind of our final check before we actually get into the units. We want to make sure we can catch anything that comes up before we actually get in the water. And some places like the Bahamas, we had lots of different rebreathers. So you imagine, there's so many, if you look at this checklist, for just even not knowing about rebreathers necessarily, there's a lot of different failure points with rebreathers. So we have to bring a lot of different backups with us in case something breaks in the field. We can repair it using spare parts. And then it's time to transit and go to our dive site. So either loading everything up in the truck or going out on the boat. So we travel very light, as you can see. And then our briefings, we have a very thorough safety briefing we do with our boat crew as well. Sometimes we have 2 boats, considering all the stuff that each diver has to carry, and other considerations with the aquarists that we're collecting live specimens. One of them is how we communicate to the surface. So when we're doing a 6-hour dive and we have a mandatory decompression obligation, we can't surface and say, hey guys, we're okay, we're right down here, and go back underwater. We have to communicate them using different techniques. So this is Meridius deploying a surface marker buoy, and this is a red marker, so we've already briefed our boat crew that a red marker means the operations are normal. Everything is unremarkable. We did our work. We have started our decompression. We started ascent, and we'll be out of the water at our predetermined time, which is we established in the briefing before. If there's a problem in the water, we have a yellow marker buoy that all of us carry, and we can deploy that, and that means I'm having a bad day. Please send Mark or Marina down, our support divers, and have them bring some more gas for me to breathe. So that means something went wrong with our rebreather. We have to bail out or go off the rebreather and then resort back to regular open-circuit scuba. So all the cylinders that in the back here you can see, these are all of our bailout gases. So one of the cost benefits of rebreathers doing technical dives is we don't use this gas. It's only in contingency when something goes wrong, then we resort back to good old-fashioned scuba. So at 10 o'clock, we have our final suit up and dive. It takes us about, somebody asked me once, how long does it take to get in the water? It takes about an hour, just from all your checks, everything, make sure everything's finalized, put the units on. The units weigh about 85 pounds, fully dressed, ready for a deep dive. So it takes a little bit of effort to get into the units. And then we have a full pre-dive checklist, make sure everything's open that needs to be, make sure everything is where it needs to be. Our set points and our electronics are programmed to where they need to be. So we do all this with a checklist, and nobody proceeds unless everybody has gone through that one point and nobody's distracted. So we take safety extremely seriously. And then it's time for the dive. So we actually go and do our dive now, and we spend about 15 minutes to an hour underwater. So really our bottom time depends on what work we're trying to do, the objective. Are we doing transects, trying to learn about the fish communities there? Are we doing photography or just scouting? Or are we doing collections. So that really depends on our objective plus our depth kind of influences our overall dive time. So we're doing a 500-foot dive. We only have about 15 minutes at bottom to have a 5-hour decompression obligation. So the deeper we go, the longer we have to off-gas now in order to release all that inert gas we absorbed from our bottom time. So as you can see, this one was in plow. I had a relatively sharp descent along the wall on the bottom for a blink of a second, 15 minutes, and then collecting an undescribed species. And then we came up off our decompression at various controlled stops. So we can't descend right away. It is a mandatory decompression. So we follow different depth intervals, and we do stops for about 1 minute, 2 minutes, and it gets exponentially longer the shallower we go. And then sometimes we're doing a transect. So this is myself here doing a video transect in the Bahamas. We're trying to categorize the benthic community and have this information be available to other researchers. They want to see what these communities are like. And this is Hootson doing a 500-foot, a transect at 500 feet looking for fish. And here, actually, I have a video. There we go. So this is one of our transects we did in Guam. So this is through my mass camera. We see we're about 300 feet here. And throughout the transect, we're looking at the different fishes, and we're trying to identify them to species, not just redfish, bluefish. It has to be scientific. We want to know what species of fish we're looking at, which can be problematic in itself, considering I've done some transects, and none of the fish have names yet. So all of them are undescribed. So you have to make your best guess of what genus it is, or Trima, species new, blue, and describe it best you can. So we deploy these 25-meter transect lines, count and size all the fish in our swath area, and then we're done with the transects. We can either repeat at the same depth or start our ascent doing more transects and fish surveys. And occasionally we were treated to these treasures, such as this massive gorgonian. Who knows how old that was, but you'll see other photos later on from Guam that had nothing of comparison in the shallower community. So it's unfortunate that the deeper we go, the less anthropogenic effects are present, so we're seeing more of these remarkable features. So our decompression is going to vary from 2 hours to 6 hours, depending on how deep we go, how long we're staying on the bottom. One of our longest dive is 6 hours. We did that in Palau, trying to collect some new species there. And we spent 45 minutes, I believe, at about 500 feet or 450 feet. So that equates to 6 hours of decompression. So it's a lot of time in the water just for 45 minutes on the bottom. But we still want to be productive. We want to do transects. We still can learn a lot about. It's not just floating in blue water, hopefully, aimlessly. We're trying to do transects and other activities. But then I get asked frequently, what do you do for 6 hours in the water when you can't go to the surface? Everybody has their own different things they like to do. We try to be productive as best we can, doing science, doing experiments. I like to do some kind of herbivore observations. I'll follow parrotfish for 15 minutes and write down what they're eating, what they're not eating. But we do get hungry and thirsty, so we bring hydration packs with us underwater so we can take the mouthpiece out and drink water, stay hydrated, and we can bring applesauce or bananas to eat. So it gets hungry when you're in the water. When you start at 10 o'clock and get out of the water at 4 o'clock, it gets hungry. So you have bananas, make great little pocket-sized snacks to eat. And then after our dive, we have a thorough debriefing of what happened, what we can do better to improve on, and then we basically reset for the next day. So we rinse our gear, process our samples so we have fish specimens we're going to catalog, and then we start our next dive. So this analyzer says, it's kind of a snapshot of what the mix we're breathing. So this is 5% oxygen, 80% helium. So we analyze our gases, make sure we know what we're breathing. We pack our carbon dioxide scrubber. I like to have a little fun when I do mine, so I use a SpongeBob golf ball, because otherwise you waste all this scrubber material down this perfectly sized hole, so you just plug with a golf ball, and it's a nice little hack when you do your scrubber preparation. And kind of going forward what I said about samples, this is our submersible container for ascending specimens, or the fun term I like to use is the fish decompression chamber. This was just published a few weeks ago, actually. And what our academy divers and aquarists developed is this portable chamber. You know how divers need to chamber if they have decompression injuries. we developed a chamber to decompress fish and other organisms when we bring them up from depth. So we have a new species potentially. It would be great if it was alive and not, unfortunately, having some barotraumas from bringing a fish to the surface right away. You've seen pictures of cod and their eyes are bulging out of their head. That's from a barotrauma, those decompression injuries. So with the chambers, we can put these fish in these little capsules and then pressurize them with a little bubble of air. And then from there, we bring them to the surface. Our Aquarius team or our second boat can then attach the plumbing to the chamber and then take it back to the facility where it can get cycled with fresh water through. And then over the course of 2 days or so, the fish can off-gas in a controlled manner with the Aquarius supervision. And the traditional way of doing this was needling. So if you catch a fish for the first time, as you bring it up through sequential depth, so say you catch a fish at 500 feet, you bring it up to 200 feet per se, that 300-foot depth change is a lot of change in pressure. So that swim bladder is adapted for where it was living, so 500 feet. That as you ascend, that pressure is going to expand or decrease, and the gas is going to expand the swim bladder, and it's going to become very floaty. So it becomes very uncomfortable. The swim bladder can press against the vital organs and cause the fish to die or suffer. So the other way, the old school method, and was still largely used, is using a hypodermic needle to needle the swim bladder and let a controlled amount of gas leave the swim bladder. So it's very stressful on the fish, and I think there's somewhere on upwards about 50% mortality rate when this happens. So through our paper and through this method, we've had a lot of success, upwards of 85%, 90% survival rates from collection to San Francisco Aquarium using these methods of using the chamber techniques. And one of the exciting things about these depths we're going to and the species we're collecting is we do find new species. So this was published about a month and a half ago in Zookeys, and this is one of the new species we collected from Easter Island. And we found, we kind of had it easy because the last team that was there with Jack Reynolds' team, they were diving to 200 feet on air. So we had, going into this, we knew that anything deeper than 200 feet was a high probability of being a new species. So this one, I believe we had 5 or 6 new species. And this one was a perchlet called Pletrantheus, and a little bit into the nomenclature behind Ahia Hihata, which is the name we gave it. We wanted to pay homage and respect to Rapa Nui and Easter Island. So this is a Rapa Nui name, which translates into the last light of day, because it reminds us of a sunset through its vibrant colors. So we named the fish in respect to that. But now let me take you through the new species process and what it takes for us to describe a new species. So step 1 is the collection process. So this is myself catching a new Anthias at Easter Island. And so we have our little butterfly nets and everything. And you notice for all the equipment we're carrying, all the thousands and thousands of dollars, still the best way we found to contain the fish is a large jug with rubber bands. So that's our containment vessel for this, at least for here, what we did to bring the fish up. We weren't using, this trip, we didn't have the resources to do live collections, so we unfortunately were collecting with the intent that these fish would be killed at some point for preservation into the Academy's collection. So with the fish we collect, we then have to catalog the fish, describing the species if we know it, or as best as we can describe it. And then we prepare them to photograph for preservation. And so we use this technique called pinning, and we take the pins and we try to not damage the morphology or the beauty of the fish itself and not damage any fins. So we put pins on the spines of the fish, so they're at their full extension, so anybody can ID them very easily. The fins aren't hiding, their spines aren't hiding, we can see them very easily. And then we use a formalin solution to kind of harden and preserve the fish as well. And then once the fish has been kind of resting in this in the state here, we then can photograph the fish. So we have our own special glass aquarium that we prop the fish, and then using lots of light and a nice camera, we can get these beautiful images of the specimen we're collecting. A little backstory, this is Pletrantheus. As a kind of inside joke, we call this Jim Joe Bob, because he's a new species as well. He's undescribed, so not us, but some colleagues of ours have collected it, and it's kind of in the queue and the hopper to get described. So until then, for surveys, we see lots of them. We have to give them some name, and so we nicknamed him Jim Joe Bob as our Anthias fish. And now a little bit, I don't have too much time to talk about the full process, but now once we have the specimen, once we photographed it, the next step is to kind of get some more information about the fish itself. So we take a sample from the gill rakers, behind the operculum. And the reason why we do that, it's a great source of DNA and it doesn't damage the morphology of the fish. So we're not cutting fin clips off that damages the image of the fish. For future studies, if somebody wants to review the fish later on, we're not harming the morphology of the fish. So we can grab a sample of tissue from the gill rakers, and then we look for mitochondrial DNA. And particularly, we're looking for the CO1 gene, which is in the grand spectrum of DNA that lives inside mitochondria, inside one cell that lives inside the hemoglobin. We take this little segment, and then we can use that and run into a comparison through our DNA sequencing techniques, and gives us kind of a barcode. So the same as you were to go to a grocery store, and they're running, you're at the checkout line, your cashier is running the barcode through the various items in your cart. It has this particular barcode that makes it unique and identifiable to other things in the grocery store. Same thing what we're doing for fish, an example. We're taking this little barcode from this entire sequence of genetic information. We're taking this little barcode of information, and then we can compare it to other similar species. So once we run that through the database of what's available and what's been analyzed by similar species, we then can identify ones that are closely related. So this is a radiograph, kind of an X-ray of the skeleton, and we can clearly see the different spines and ray fins of the fish. And so using our DNA barcoding and sequencing, we can look at other similar species, other organisms that are known and documented that have already been through this process, and we can compare them to. And then from our end, all we're doing now is arguing why ours is new. Or if we're finding anything that's unusual, but maybe it's a different color, or maybe it has different features, we then can compare it to closely related species and compare it. So this is Pletrantheus winiensis, which is the closest known relative to this species, and so we can make our arguments and compare ray fins and so on morphologically. So from there, throughout this process, we submit the paper to a scientific journal, and many months of back and forth editing. Sometimes there's content development. The publisher wants us to do more studies as far as more measurements or more descriptive information. But once that's been done, it's then passed through our peer review process. It's then published in a scientific journal. And this is not that paper in particular, but this is one of our similar papers that Hudson and Louise published. And it made the cover of Nature last year. So I want to give a shout out to them and the incredible work that they continue to do too. So that's kind of overview of our new species that we have, and it's still an ongoing process. We have about 5 or 6 at least of fish that are next up onto our docket of processing. But what we have going on right now is our ARMS project, and that's our artificial reef monitoring structures. So the ARMS are these little PVC arrangements that are set up in like little pyramids. And so what we've been doing at different locations, such as Guam in this case, or the Philippines, or in Palau, is we're deploying a set of 3 of these structures down at different depths, and then these are going to basically grow into mini coral reefs over the course of 2 years. So we deploy 3 of them to have replicates and have a little bit more information than just one. We deploy 3 of them at depths of 100 meters, 50 meters, and 10 meters, and over the course of 2 years, all these reefs will develop very uniquely, specific to their depth zone and habitats, which makes it a bit of a challenge when we're taking these heavy structures. So this is Meridius with a scooter here trying to manage 3 PVC structures and all the other stuff we have to carry. So it's a very strenuous process when we can't just drop them right down where we want them to and then nail them into the structure we can come back to and retrieve them 2 years later. And when we do retrieve them, basically we just have a lot of information and there's so much data to process that the most, unfortunately, non-elegant way to process them is to scrape off all the slates, put it into a blender, and then just do lots of DNA sequencing. And then from all the information, we can get a very accurate biodiversity assessment of these different ecosystems. I want to kind of end now on a little bit of comparison of why these comparison of these mesophotic ecosystems and shallower ecosystems to show how beautiful they can be, but also how significant they can be. So this is a photo taken at a coral reef in Guam at 92 meters, so about 300 feet. And this is the same reef, but at 14 meters. So in Guam, there's been lots of over-harvestation of different fishing and all kinds of different benthic organisms. So Guam, unfortunately, has lost lots of their coral reefs through over-harvesting, but yet they still have these beautiful ecosystems, but because they're undisturbed, they hold these keystones of biodiversity that maybe in theory someday could replenish the shallower ecosystems. And unfortunately, even though we're finding reefs, part of the excitement that we get from doing these dives, we're diving on reefs that no human's ever seen before, but yet inadvertently, almost every trip we go to, we'll find trash or some sort of debris. So even though you might be out in the middle of nowhere on a fishing boat and somebody throws a beer bottle over the side, that does have an impact on some ecosystems and some organisms. In some cases, like the Philippines, there was just so much debris everywhere, but some species like these ctenophores, we call them sea peeps because they're kind of funny looking, they have these nice little Easter colors, made habitats out of fishing lines. So there's been such an exacerbated problem with pollution that these ecosystems and habitats are already adapting to our human effects on these reefs. So that kind of overlies the importance of these ecosystems. But the work we're doing is very exciting, and I hope I entertained you tonight. So this time I'll take any questions you might have.
Tyler, thank you. You're an excellent presenter. Who has the first question?
Okay, Ty, in all the tremendous work you've done and all the experiences and different travels, what would you assess the direct degradation of the reefs? What is the biggest impact in your thinking to the rest of the planet? I mean, a lot of our reefs are dying. We know that. So what would you, can you sum up what you think is the biggest impact we're looking at planet-wise?
The biggest impact to our coral reefs, planet-wise. There's a lot of confounding variables that influence reefs, and we're seeing that humans are having an anthropogenic effect on reefs. Be it, one example, we were diving the reef I was showing you here. This was taken about 200 yards off of a strip of hotels. So the clues suggest for the levels of algae and lack of coral is that there's a chemical imbalance in the water. So pollution, sunscreens, all those kinds of things, they're all compounding and cascading out to have really profound detrimental effects. So things like the oxybenzone sunscreen movement that we're seeing, all these low things are having a tremendous overall effect. So maybe not just sunscreens having the biggest effect, maybe it's not just plastics in particular or our use of carbon dioxide. I think overall we as a species of humans are having a profound effect on these ecosystems. So it's all of our duties to have, just look back at the little things we're doing, the things that we can do every day, like change our sunscreen or recycling, all those little things. If everybody does it, it will make a huge impact into our reefs.
Next question. Anybody? Okay.
Thank you. I may be confused, but it seemed to me like some of the pictures you showed, I think about 300 feet, it looked like there was quite a bit of natural light. I thought at 300 feet things would be pretty dark, but not so, huh?
Yeah, so if you're saying that at some places 300 feet, they look pretty light. So it largely depends on where we're diving. So in the Philippines, for example, where there's lots of runoff, lots of pollution, there's all the suspended sediment in the water. There's a picture of me at home there's a picture of me doing a translate at 300 feet. It looks like I'm on a night dive. I mean, there's just virtually no light penetration. But areas of Easter Island with the very clear blues, you're seeing all the light. There's a very little suspended particles in the water, so you get lots of light penetration. So, and that largely kind of sets where the boundary of mesophotic reefs begin. So if we have lots of light that's penetrating down, reefs, even our scleractinian reefs, like the hard corals, they can actually grow and be successful at 200 feet. But you take that same coral and plant him on our reef, same temperature, but different sunlight characteristics, he's not going to be able to thrive in that community because there's not enough light penetration. So all these different things influence the reef habitat.
This seems like a pretty specialized subject. How many people do you know that are studying the 200 feet to 500 feet?
There are, so you're saying there's a lot of specialized field. There are plenty of technical divers that are diving to 200 feet, 300 feet in excess. As far as scientists that are doing this sort of research, that are doing these dives in person, we've estimated no less than 15 in the world. So it is a very specialized field. There are plenty of other researchers that are doing this with ROVs and doing them with submersibles that have the funding and capabilities to do so. But we like being able to do this in person because we can learn so much more from a reef. And for example, if I'm doing a fish transect at 300 feet or so, the fish aren't going to just stop and be picturesque and display all their fins and stay still if you identify them. A lot of times I have half a second to see a tail fin and know what fish that is. And that comes from lots of studying and reviewing your fish IDs. But on camera, on an ROV, there's no way I could be able to identify that fish. If I saw a glimpse or through a pixel, I wouldn't be able to identify that. So there's lots of benefits of keeping the human component into the sort of exploration work we're doing. Versus, yes, you can argue it's much safer to do this behind a camera screen. You don't get that immersion effect that we're getting through diving.
Other questions?
Hi, Tyler. My name is Val, and I think I remember you as a VolunTEEN here at the aquarium. My question to you involves your gaining this knowledge that you have now, which is very impressionable. Were you a diver when you were a VolunTEEN? And if you were, how did you go about gaining this experience that you have now? I think a lot of people who might want to go in the field or have kids or grandkids who might want to follow your path would be interested in that.
Thank you, Val. Back when I was at VolunTEEN at the aquarium, I think I had just gotten certified. But when I was 16, I had no ambitions of diving to 500 feet. That just was oblivious to me. So I attribute my success into doing this from a relatively young age is I always looked terminally and worked backwards. So for me, it's kind of funny to think of somebody that's 20 years old doing this, but I look back, if me being 8 years old, just retiring, what kind of career would I want to have to make an impact? So I thought, maybe I want to be a teacher, maybe I want to be a professor. So then I worked back, what kind of research would I have done as a professor? Well, what's new and exciting? And then I found this sort of field. Okay, so these guys are finding 12 new species per hour of dive time. What do I need to do to do that? And I found these guys doing closed circuit rebreathers. So I say, okay, I need to get to there. How do I get to there? And so then I basically climbed the ladder for training, but I kind of started backwards and worked to where I am right now. So for anybody that wants to pursue this kind of field, I recommend always thinking of the end in mind. What am I going to do now that's going to make a difference to me later on? And kind of goal setting is what I did. So a lot of things my parents taught me from a young age to write your goals down on a big piece of paper and put it up on your wall so you can see it every day. And that's what I did. It's as corny as that is, but I worked backwards, and that's how I got to where I am.
Very good advice. Any other questions or comments? No? Well then, Tyler, again, thank you for a wonderful presentation. We hope you'll come back again soon.
Thank you. And thank you all very much for coming.